All right, Steve here, coming to you in topic 9 again. We're working, remember, in topic 9 about measures of spread, different ways we have of putting a number on how spread out or consistent a data set is. And in your previous activity, we worked on a range, an interquartile range. In this activity, activity 9-2, the goal is to get an understanding of the standard deviation. Okay, mostly focusing on the calculation of it. Okay, the authors of your textbook also discuss something called the mean absolute deviation, and we'll mention that in passing, but that is less important for our purposes. Okay, so let's just take a very quick look at the definition of the standard deviation. Okay, what the standard deviation measures, very roughly, is it measures the square root of the average squared deviations from the mean. Okay, that is a mouthful. And if you look at that formula looks very scary. Okay, all right. And there is some work to do, but it's not so bad. We'll talk through it in this example, and then I'll give you a link to some other videos you might want to watch if you need more practice. Okay, all right. So when you're calculating the standard deviation, the first thing you need to know is the mean. Okay, the average of all your observations. That's x bar, right? Remember that notation? Okay. And then what we do is we find how far each of our observations is from the mean. Okay, that's what we call the deviation from the mean. Okay, and so we calculate this quantity xi minus x bar, how far each observation is from the mean. We square it. Okay, and then this Greek letter sigma here means add them all up. So we're going to add up all these squared deviations from the mean. And then we're going to divide not by the number of observations, but by one less than the number of observations. And we do that for various statistical reasons. But basically what we're doing is we're averaging the squared deviations from the mean here. And then to get back to our regular units, we take the square root of the whole thing. And that gives us our standard deviation. Okay? That's a lot of work, and it's a little hard to think about out of the context. So what we're going to do is we're going to look at an example. Okay, so we're going to go back to our developing life expectancies example. Okay, so if you remember, we have these two countries, Botswana and Papua New Guinea. And what we want to do is we want to calculate the standard deviation and use that as a measure of how consistent those data sets are. Okay, so the first thing we need to do is we need to calculate the mean life expectancy if we're going to do Botswana. Okay, we're told, they did the work for us, they found the mean life expectancy for Botswana is 54.8 years. Okay, so my table's a little hard to read there, so I've got a blown up version here, and we're going to use that. Okay, now you remember from that complicated looking formula, the first thing we had to do is we had to calculate the deviations from the mean for each of our observations. Okay, so for example, okay, if the mean is 54.8 and my first observation was 63.5, I do 63.5 minus 54.8, and that gives me 8.7. Okay, and so in that notation at the beginning, that's like doing x1 minus x bar and finding that value. That's the deviation from the mean, 8.7. Okay, and then we do the same thing for all these other observations. 63 minus 54.8 gives 8.2. 62.7 minus 54.8 gives 7.9. Here's one we have to fill in. 56.6 minus 54.8 is 1.8. Okay, and then these other observations are below the mean, so the deviations are negative. 52.5 minus 54.8 is negative 2.3. Okay, and so on. And if I look, 49 minus 54.8 is negative 5.8. So that's its deviation from the mean. Okay, now Why do we care about this at all, right? So that's a great question, all right? So let's just look at our dot plot for a second, okay? So ignore Papua New Guinea and just think about Botswana, right? So the mean for Botswana was 54.8, so right about here, okay? So now one way you can measure, you might think to measure how spread out a data set is you can talk about, well, how far are the observations from the mean, right? So lots of observations for Botswana are a good long way from the mean, right? So you might think, well, a reasonable way to measure or to try to measure how spread out the data set is to look at all these deviations, right? How far an observation is from the mean, okay? And then if you took the average of all those distances, that would be a good measure of how far a typical observation is from the mean, and a measure of how spread out the data set is. Now the problem with just calculating the deviations and then averaging those, well, you see, if I add up all these numbers we have, 8.7 and 8.2 and 7.9 and 1.8, and then these negatives, it turns out the sum is 0. Or at least it's 0 up to maybe some rounding, okay? So the point is, right, is that all these positive deviations from the mean cancel these negative deviations from the mean, because the mean is the balance point of the distribution, right? It's precisely the value so that the deviations on the high side and the deviations on the low side cancel each other out, okay? So we can't just use those deviations and average those, okay? The mean absolute deviation, and here I just want to mention it briefly, what we can do is we can take the absolute value of the deviations, and so instead of measuring the deviations, we'll measure the distances, right? So the observation that was 2.3 years below the mean, we'll just say it's 2.3. And then we could take the average of those, and that would be a way we could measure how spread out our data set is. And that would be our mean absolute deviation. We're not going to care about that. The mean absolute deviation is a very natural thing to consider, but it turns out not to be as mathematically useful as the standard deviation, so we're not going to do that, okay? Instead, what we're going to do is we're going to look at the squared deviations from the mean, okay? So the way we'll make our deviations all positive, instead of taking their absolute value, is we'll square them. Okay, so here, for the year 1987, when the life expectancy was 63.5, that was 8.7 years above the mean. That was the deviation. We're going to square it, and we get 75.69. Okay, and then we do that the same thing with the second observation. The deviation from the mean is 8.2, but when I square it, I get 67.24. Okay, and 7.9 squared is 62.41. And then 1.8 squared is 3.24. Okay, and then these negative values, negative 2.3 squared is 5.29, and so on. My deviation here, the one I have to fill in, the deviation in 2005 was negative 5.8 years below the mean. I square that, and I get 33.64. Okay, all these squared deviations are positive. We'll add them up, and when we add them up, we get 368.9. Okay, now we could average them, and we almost average them. But to average them, we would divide by 9. For various statistical reasons, we don't divide by 9, we divide by 8. So if I look at 368 48.9 divided by 8, I get, need my calculator for that, I get 46.1125. So I get about 46.11. Okay? And then the last step in my calculation is I take the square root, and that gives me the standard deviation. And that gives me about 6.79. And the units are years. Oh, a little hard to see. Okay, so let me go back one more time to our definition of the standard deviation, and you can see what we did, right? So we found our mean that was given to us. We calculated the deviation from the mean. We squared the deviations. We added them up. We divided by one less than the number of observations. And then at the very end, we took the square root. Okay, and that gave us the standard deviation. That's how we do the calculation. All right, so we're doing really well here. If you're keeping track, we found the standard deviation for Botswana, their life expectancies was 6.79 years. Okay, and on our list of tasks in activity 9-2, that takes us up to step G, right? That's Botswana's. Okay, then it says use technology to verify your calculation, and use technology to calculate the standard deviation for Papua New Guinea. Okay, so that's our next step. Okay, so here's our data set again. Okay, our raw data set. And the thing about standard deviation is it's a nasty calculation to do by hand, but technology works actually very well here. Okay, so that's how we're going to go after it right now. All right, so I'm going to use my my TI-84 calculator to do this. All right. If you have an 83, you can do it there as well. And what I'll do is I'll use a stat tool. Okay, so I'm going to use stat, edit, so I'm going to hit enter. Okay, and then you have these lists. Okay, and if you have stuff in your lists, you can delete it pretty easily. You can go up here, hit your up arrow, hit enter, and then just hit clear and enter. Okay, and then we can just enter our data. So I'm going to do 63.5, 63, 62.7. Move that up. 62.7, 56.6, 52.5, 48.9, 46.5, 49, 50.6. Okay, so those are my 1, 2, 3, 4, 5, 6, 7, 8, 9 observations for Botswana. Okay, I just put them in a list. All right, and then I'll go back to my home screen, so I'll do second quit. All right, and then I'll do a stat calculate, and then one variable statistics. It's going to hit enter, and it's going to calculate the one variable statistics from list L1. That's exactly what I want. I'll hit enter, enter, and calculate. Boom. Okay, gave me the mean. There's my mean, 54.8. Gave me the sum of the observations. I didn't care about that very much, and the sum of the squared observations didn't care very much. But oh, there we go, SX. Okay, there's my standard deviation, 6.79. By the way, if you keep scrolling down, it gives the minimum, the first quartile, the median, the upper quartile, the third quartile, and the maximum. So it gives you a quick way of calculating your range and your IQR as well. Okay? So that's how we calculate it. Great. So Botswana's standard deviation is about 6.79 years. Okay, let's do the same thing for Papua New Guinea. All right, so I'm going to go back to my stat edit. Okay, I'm going to clear my list. So I'm just going to hit clear. All right, and I'm going to enter 53.9, 55, 55.7, 56.2, 56.5, 56.8, 56.9, 57.2, 57.4. Okay, and then I can do my stat calc, one variable stats, enter, 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 and there we go. Okay, the mean was 56, the mean life expectancy was 56, and the standard deviation 1.13. Okay, and remember the whole point of this, right? The whole point was trying to find a numerical measure of consistency, right? So what this says, Botswana's roughly the square root of the average squared deviations from the mean. For Botswana is 6.79, and for Papua New Guinea it's 1.13. Again, it's a measure that says, yeah, roughly the observations for PNG are much closer to the mean on average than those for Botswana. Okay, so that's what the standard deviation is telling us. Okay, last thing here, right? They ask us to make a conjecture as to why the variability in Botswana's life expectancies is so much larger than PNG's. I think we already said that. It could be a disease or perhaps a war could have caused the dramatic change in Botswana's life expectancies. And then the final question, it says, suppose that the 1987 life expectancy for Botswana had been incorrectly recorded as 83.5 years rather than 63.5 years. Okay. All right. Would you expect this to have much effect on the range? How about the IQR? How about the standard deviation? Okay, remember what we said about the range and its susceptibility to outliers? Yeah, that 83.5 is going to make a difference, right? How about on the IQR? No difference at all, right? Because the IQR is resistant to outliers. What about the standard deviation? That one you might have to think about, right? It's going to change the mean, right? And we know the mean is susceptible to outliers, right? So there is going to be an effect there as well. Okay? That makes sense? So the range and the standard deviation are susceptible to outliers. The IQR is very resistant. All right, good work. That's a lot of calculation to do. I will include a link to other examples of standard deviation calculations if you need to practice.